So I'd like to start by little recall of what we did last time, and highlighting the parts which will be used in today's lecture. So we're still doing the Teichmüller space. Of punctured surfaces. So the Teichmüller space was denoted by tau of sigma. Then we define the decorated version of it. And I will not recall what was it geometrically, but the essential thing is that there was a projection from the decorated space to one non-decorated space. And then we had so we defined an ideal arc, and based on that, we defined a lambda length, which was a positive valued function on the decorated Teichmüller space, lambda length. And based on that function, we define the map lambda. So we have chosen an ideal triangulation. And based on that choice, we defined another function depending on that ideal triangulation, lambda tau. But this time, it was a function with values in the certain power of R positive. And that power is given by the set of edges of tau. So tau 1, a set of edges. Of tau. And this was defined just as a collection of lambda lengths. So lambda tau of m tilde. So this I interpret as a set of functions on the edges. So when we apply this image to an edge in here, we get a positive number, and this is given by the lambda length of E, referring to that. Yeah, and then the Pender theorem consisted of 4 parts. It said the following things. So lambda tau is a homeomorphism. Second thing was about Ptolemy, I guess. Yeah. So if tau and tau prime are related by a flip of a diagonal, A, B, C, D, E, A, B, C, D, F. So this is in tau. This is in tau prime. So if we have 2 triangulations which differ just in one diagonal in one quadrilateral, then the theorem tells us that the corresponding coordinates or positive numbers are related by Ptolemy relation. EF equal AC plus BD. This is called Ptolemy relation. And third, we identified the image of the Weil-Peterson symplectic form. So if we pull back, so the Weil-Peterson form lives in here. So we first can pull it back by phi. Weil-Peterson. Then we have a homeomorphism lambda tau. So now the pullback by phi of Weil-Peterson form lives in here. So then we can push forward or pull back by the inverse of lambda into here. So we pull back lambda tau inverse. The result will be something living in here. And here we have an explicit set of coordinates. And this form now is written explicitly like this. Sum over all triangles. And if we have 3 sides labeled ABC, this time we interpret them as coordinates. Then the contribution from that triangle is given by 3 terms, dA dB over AB, and plus cyclic permutation. Okay, let me write it. dB dA dC plus dC dA. And the first part was about identification of the image of the Teichmüller space. So M tilde phi of M tilde was equal to phi of M tilde prime, if and only if there existed a function alpha at the vertices, positive valued function at the vertices, such that lambda length of M prime at E is given by a scaling or at 2 ends by function alpha. Lambda length at M tilde. Here we have a E with Pi and Pj as the endpoints. So that's what we did last time. We didn't prove whole thing, but we outlined essential parts. For example, the inverse of lambda tau has been described explicitly. On the base of that inverse, part 2 was very easy. And for part 3, we don't know Weil-Peterson form anyway, so we just accept the formula. And part 4 is, we leave it as it is because it is not very important for the sequel. Now I'd like to start moving forward based on that. So we continue with a definition. If you have questions to that part and maybe to whole material of last time, please ask now. Definition. So pointed ideal triangulation so what is it? It is denoted tau with a dot, is an ideal triangulation where each triangle provided with a distinguished corner. With a distinguished corner. So we have seen already this similar notion under the name of decorated ideal triangulation, but here we don't order the triangles. We just mark a corner in each triangle, but not more than that. So it is some kind of half decorated ideal triangulation. And based on that, we do the following. So we associate to each pointed ideal triangulation two maps. So to each pointed ideal triangulation, so that we associate two maps. And I put them all together. So we pick up a set of functions with values in R2, positive R2, and it is defined on the triangles. Okay, I keep using this notation. Remember that xi is a set of I-dimensional cells if X is a CW complex. So this means that we have a pointed ideal triangulation, and we associate a couple of positive numbers to each triangle. And now we have two functions which we call R tau dot and S tau dot. So for one function, it is a target space. For another one, it is a source space. And for the first map, so what is a source space? It is a set of positive numbers on edges. So here I don't put dot because it is clear that if we raise dot, it means that we forget about marked corners. And the presence of marked corners doesn't matter here, so I don't put dot here. Okay, so this will be a function like this. And here, the target space will be the first cohomology of the surface with coefficients in R positive. Okay, so how we define them? So for the first R tau dot, the definition is by picture. So if I have a triangle with variables A, B, C on the sides, and we have a dot in one corner, then our map R tau dot associates to this configuration a couple of numbers inside this triangle. So I keep the marking, and then here I put two ratios, and the choice of the corner tells us who is the denominator. So in these two ratios, the denominator always will be C. And then A and B are two numerators, but for some strange reason, I start from right to left. So I write B, A. Okay, so that's the rule. That's done. And then for the second map, I do the following. So S tau dot. So what is it? So we have to pick up a function on triangle. So let us call it X. And now this should be a cohomology class. It should correspond to a cohomology class. Cohomology classes are represented by functions on the closed curves. Right? So we put a closed curve as an argument. And now this is going to be a positive number. Now I write this positive number as a product of contributions from triangles. And the contribution from triangle is given, so I write it like this. So I evaluate x at this t. So this is going to be a two-component vector with positive components. And I put it some evaluation on gamma, and now I will say what does it mean, this part. So where x t gamma is given by different forms of the contribution. For example, x1 over t divided by x2 over t. So the ratio of two components of t if our triangle, this is t, if the curve gamma passes through that triangle like this. Okay, we put gamma into general position so that it intersects triangles. And if we encounter that triangle T is intersected like this, then the contribution here is given by this ratio. Then we say x2 of t, the contribution is x2 of t if the contour goes through t like this. And we have a x1 of t if the contributions like this. If the intersection is like this, and the contribution is 1 if the contour does not intersect our triangle. And of course, there are three more cases if you switch the orientation. Then, of course, you switch the number to its inverse. And yeah, so if you make a closed curve sitting just inside one triangle, so the product of these three is 1, so it is consistent with elementary isotopy. Yes?
Surrounded by x of t mean just this pair? V over C?
Yeah, x of t is x1 of t, x2 of t, because x is a function on triangles which takes two positive values. Okay. These two positive values are here.
Thank you.
You're welcome. And of course, it has to be checked that this is independent of the choice of the contour, which represents the same class. But this is not difficult to check, after all, using these conventions. And now I formulate the main theorem. About these two maps, which is a much more easier theorem than the Pender theorem. Which tells the following. Yeah. So the first part, the following sequence of group homomorphisms is exact. So what is the sequence? So we copy the string over there. So R positive 2 tau dot 2 mapped to H1 of sigma R positive R positive tau 1. Here we have a R tau dot, S tau dot. And we complete this from the left by R positive, given by constant maps, delta to constant maps. So which means that a function, the image of delta of a positive number corresponds to a function which takes this positive number value on each edge. One here and one here. So group homomorphisms is clear because we have a functions. This is a group, abelian group, for evident reason. But here we have a functions on an abelian group, multiplicative group of positive numbers. So it is an abelian group. Then we have a second part which concerns the Weil-Peterson form. So if we take the description of the Weil-Peterson in Pender coordinates, lambda coordinates, phi star omega Weil-Peterson. So this is so this object lives in here. Now we say that we can pull back by R of tau dot something in here to get the same here. So we equate it R dot star of omega tau dot. And now we have to say what is omega tau dot. Is given by sum over triangles. So we have a function x, x1, x2, sitting in that triangle. And the formula is this, dx2 wedge dx1 divided by x1, x2, x1. So you can notice that so omega tau dot is very simple thing. It is a canonical symplectic form sitting inside each triangle. And the third part concerns the change of pointed ideal triangulations. So this is the longest part. So for any pair of dotted pointed ideal triangulations, tau prime with points, there exists unique but which are not just homeomorphisms, they are rational diffeomorphisms, but never mind. Homeomorphisms are f of tau dot prime, which relate to spaces 2 dot prime, which order of the, yeah, so I put the same order, 2 R positive to R2 tau dot prime positive. Unique homeomorphism such that the diagram okay, so what we have here? So we have tau tilde of sigma, decorated Teichmüller space. We have lambda tau, which arrives to R positive tau 1. Then we put R tau dot to arrive to R positive 2 tau 2 dot. Okay, so this is one possibility. Then we can go do the same with lambda tau prime. R positive 2 tau dot prime 2. And then we can close this diagram by adding f of tau dot prime. And yeah, so this is one thing, and we put in the same part, and the pullback of the symplectic forms omega tau dot prime. So the pullback by this map of omega dot tau prime gives us omega tau dot. So the symplectic forms are consistent. And here we describe two particular cases of that. In particular, if tau dot and tau dot prime are related by, so we distinguish two cases. Case A, so if they are related by a change of the distinguished cone in one triangle. Change of the distinguished corner in one triangle. If then, yeah, so let me write first the change of the corner. So we have T0 here. So this is tau dot so the same triangle, but this time in tau dot prime. Then we have a formula. We have a formula. So f of tau dot prime. So this function f. We act on x in here. So we should get a function in here. And this is a function on the triangles. So we insert a triangle as the argument. Now we have to get a couple of numbers. So the formula is the following. So it will be same function x of t if t is distinct from t0. And x2 of t divided by x1 of t, comma 1 over x1 of t, if t is equal to 0. Okay, that's one particular case. And then case B, so if tau dot and tau dot prime are related by a diagonal flip, and this time we describe the flip explicitly as follows. So I put, now you start probably recognizing pictures you've seen before, but the content a little bit different. So I put x, y inside the triangles. And then we put opposite diagonal, keep the marking intact if we rotate it clockwise. We put here u and v. This is in tau dot. This is in tau dot prime. And here so I'm not very consistent with notation. Here T0 means a triangle. Here XY means functions or couples of real numbers. Okay, please don't mix up these notations. Then we say that u is given as a certain function which I denote x dot y, and v is given by certain function x star y. So I'm now going to give you what these two operations where. So here is a x dot y. So it is a x1 y1 comma x1 y2 plus x2. So this is a dot operation, and the star operation is a little longer, and I have a smaller space for a bigger formula. So it is a fraction, and with the same denominator. The denominator is given by this second component in here, x1 y2 plus x2, x1 y2 plus x2. And here the denominator is this quadratic term with the indices switched with each other. So x2, y1. And here we just put a y2 in the numerator. So yeah, that's it. So that's a transformation. And of course, if you see the other triangles, the function is the same. So it is not detailed at this formula, but I write only the analog of that. Okay, so is it clear, the statement? I'm not very formal here, so please don't mind. Okay, so the proof is not difficult, so I am going to give it. So the part one, so which I just erased. So we remarked that in logarithmic coordinates, this is a sequence. This is an exact sequence of vector spaces. Okay, real vector spaces. And but the fact that the composition of two neighboring maps is trivial is very easy. So let us accept this. So what we do is just we check the consistency of the dimensions. So the consistency of dimensions. So we define 3 dimensions, D1. D1 will be the dimension of the middle part. I mean there is no middle part. But let me write it. Dimension of R positive twice T dot of 2. Okay, so what is this? So this is twice the number of triangles, which is twice. So the number of triangles is twice the number which enters the negative Euler characteristic, so which is 2g minus 2 plus s. Okay, that's the number, the dimension. D2. D2 is the dimension of R positive tau 1. So this is the number of edges. Number of edges is 3 times this number. So it was, I think, the exercise, right? Another day to check these numbers. Do you want me to explain these numbers? No. Okay, and finally, the dimension of H1. So how we count this? So of course we count the part coming from the genus. So it is twice G. Then we add the part coming from the punctures. So the numbers is S, but the number which we have to add is 1 less. Because if we surround all punctures by a closed curve, then we can go other side of the closed surface to make it trivial. So these are the numbers. And then if we want to check the exactness of our sequence, then we have to do what? So we have to projectivize this space, because if you look at the sequence, we insert in the constant functions. So we have to take the dimension D2 minus 1, right? D2 minus 1. Because we have to subtract the image of the constant functions. And add the D3. And this should be equal to D1. Yes?
Sorry, can I ask a stupid question about D3? So for example, if I take a torus without
Yes.
punctures,
Yes.
I should have dimension 2, right? Not 1?
Yes, but if you remember, the number of punctures in our theory is non-empty.
Okay.
So it's forbidden.
All right. Thank you.
D2 minus 1 plus D3. So what is it? So let us just add. D2 is a 6G. I spread out the multiplicative factor. 6G minus 6 plus 3S minus 1 plus D3, 2G plus S minus 1. Now let's add. So we have 6G plus 2G is 8G minus 6 minus 1 minus 1 minus 8. and plus 4s. And this is equal 4 times 2g minus 2 plus s, which is exactly d1. Okay, so on the level of dimensions, everything works fine. And taking into account that these are vector spaces, so it's almost enough. So it remains to check that compositions of R tau dot with delta is trivial, and that S tau dot is surjective. This is S tau dot composed with R tau dot is trivial also, and that will be exercise. Okay, so R tau dot delta is trivial. What is it? It's a 0. It's 1 maybe. It's a multiplicative picture. 1 and S tau dot R tau dot 1 exercise. And together with this, dimensional calculation will be enough to finish that part. Yeah, and then second part. So what was the second part? It was about symplectic form. So let us just do some manipulation for the left-hand side. So by Pender's theorem, we have this formula dA. So let me write it in this way: d log of a, okay, log of d of capital A wedge d of capital B plus d capital B wedge d capital C plus d capital C wedge d capital A, where small a is e power capital A, small b is e power capital B, small c is equal e capital C. So we take the logarithmic coordinates. Then what we collect, for example, we collect the coefficients of dA, which is the first term and the last term. dA wedge dB minus C, same ABC, plus dB, because the wedge is antisymmetric. And now we can put together two terms with B minus C. So the result is a sum of triangles ABC, dA minus C, wedge dB minus C. And now if we come back to logarithmic coordinates, so this is rewritten as a d log of A over C, wedge d log of B over C. And this is nothing else but the pullback of pullback by R tau dot of d log of x2 wedge d log of x1, sum of triangles where we specify one corner with variable x. Okay, if you look at the definition of R tau dot, then we put exactly two ratios with one as the same denominator, and the denominator was opposite to the marked corner. So here the denominator C here, so we put the upper corner as a marked corner. And if you remember, so the A was corresponding to second component and B to the first component. So that's why we put first x2 and then the x1. And this is exactly the form which we denoted omega tau dot. Yeah, and then we finish the proof after the break. So I was just told that the first part is not complete. Okay, so please think during this week why it is not complete. I will do as well, and we will come back to this next time. Okay, so now I continue with part 3. Part 3. Yeah, so, but it suffices to say that we have to check 3A and 3B. I mean, the two particular cases, because any other case is obtained by composing those elementary transformations. So 3A. So what we have? We have here ABC. This is in. So we go either by R tau dot from here, which is B over C, A over C. So this is a tau dot. Or else we go by R tau dot prime. So this time we put the distant corner here. So the denominator will be B. And now for the numerator, so the first component will be with A, and the second component with C. And can we see now? This I call X. This I call X hat. And X hat, can we write it in terms of x's? So A over B, so we easily see that this is x2 over x1. And C over B is the inverse of B over C, so 1 over x1. So that's it. (3b). So we have a picture, starting picture like this, A, B, C, D, E. And we go with lambda tau composed with lambda tau prime inverse. Oh, it's a tau prime is here. So then we go here, F, A, B, C, D. So that's what we had in Pender theorem. But now we can go by adding the markings at corners. We can go either here, X, Y, or we can go here, UV. So let's calculate. Let's calculate x, y, UV, and this will define us the map F. Now we calculate x, y, UV. So what is x? So we can put maybe also here the markings to make contact with the site h variables. So x1 should be a over e, right? E should be in the denominator. So the a over e and d over e. What is y? Y is going to be e over b and c over b. Now we calculate u. U is going to be a over b and f over b. And v is going to be d over f and c over f. Now we want, let us choose, for example, as a distinguished variable e, and then we can solve for the rest of the h variables in terms of x, y, and e. So for example, a becomes e times x1. D becomes e times x2. From here, b becomes e divided by y1. And from here, c becomes y2 times b, but b is e. So e over y1. So we have expressed 4 site variables in terms of x and y, and 1 variable on the diagonal. And now we can just substitute those expressions into the formulas for u and v. So what we have for u is a is e x1 divided by b e over y1, comma f. But now f, remember that we have a Ptolemy relation here. So EF equal AC plus BD. So we can express F in terms of AC, BD, and E. Let me write F here. So F equal 1 over E, and AC, it's E squared x1 y2 over y1, yes, plus BD, plus E squared x2 over y1. And we can simplify this to E over y1, x1 y2 plus x2. So now we substitute, so we have to put here f over b, e over y1 divided by b, y1 over e, x1 y2 plus x2. So this indeed becomes x1 y1, x1 y2 plus x2. The first of the formulas, this is x dot y, and v is likewise the d ex2 divided by f, which is e over y1 x1 y2 plus x2, comma, c y2 over y1 e divided by, again, f e over y1, x1, y2 plus x2. And we easily observe that we get what we want. Y1 goes away, e goes away, y2, x1, y2 plus x2. So this is the x star y. Okay, now that's it. That's it. So we end the proof. And we can now state the next theorem. But maybe before I go further, I make a remark. The operation x dot y is corresponds to multiplication of matrices. x1, x2, 0, 1 times y1, y2, 1. Okay, now theorem. So define V to be R positive squared. Define R to be a map from V to V given by R of x1, x2 equal x2 over x1, 1 over x1. And W, which goes V cross V to V cross V, which sends x y to x dot y, x star y. Then the triple of objects V, R, W is a basic algebraic system in the monoidal category of sets with a Cartesian product as a monoidal product. Yeah, we in the symmetric monoidal category, symmetric. So in other words, we have constructed an example of a basic algebraic system which underlies the construction of representations of the mapping class groups of punctured surfaces. And the Teichmüller theory just has led us to a particular concrete solution for that system. And this is the essence of the Teichmüller theory. So we we can now forget about the rest, just to stick with this basic algebraic system, and then it contains the full information of Teichmüller theory through the representation of the mapping class group. Because the essential thing about Teichmüller theory, of course, there are many other questions, but what interests us from the viewpoint of topology, quantum topology, is the realization of the mapping class group. And yes?
What is a basic algebraic system?
Yeah, okay, let me recall then. Recall a basic algebraic system in a symmetric monoidal category. C is an object V in C morphism R in endomorphism set of V, W in endomorphism set of W tensor W, V tensor V, such that so R power 3 is identity of V, W12, W23 equal W23, W13, W12. And the last thing is R1, R2, W21, R1 inverse, W is equal P12. And that's it. So that's a basic algebraic system. And what we have seen 2 weeks ago is that any solution of that system leads to a representation of the group point of ideal triangulations, and in particular leads to a representation of the mapping class group of the punctured surface. And now let us see a little bit why we have a solution. Of course, we can check it directly, but this is a little bit lengthy, and I would like to just show you on the set theoretical level. So if we stay in this category of sets, how we can see what is a minimal set of relations underlying this basic algebraic system. So the general structure of basic algebraic systems in set. Yeah, so of course we have if we say R of X, let it be denoted X hat, then X hat hat, so we will denote by X check, and then X triple hat will be X, right? And so X hat with check equal X check with hat equal X. Just notational nonsense, but it's easier to write hats checks than R. So this is the first property. And the second property, if we define just by this formula, then the pentagon will impose some relations on stars and dots. So let us see what is it. So W 1, 2, W2, 3, x dot y, x star y. So I apply x, x, y, z. So we need 3 arguments. This is in endomorphism of V tensor V. So we have to apply 2, 3 to x, z. So W1, 2, x, y dot z, y star z. And then we apply 1, 2 to x and y dot z. So we get x dot y dot z, comma x star y dot z, y star z. So now we take the right-hand side, 2, 3, W1, 3, W1, 2, to the same triple of arguments, x, y, z. Then we get W2, 3, W1, 3. So first we apply to x and y, x dot y, x star y, z. Then W1, 3 should operate to x dot y and z without touching x star z, x star y. W2, 3, x dot y dot z, x star y, x dot y star z. And finally, W2, 3 acts on the 2 last components. So we end up x dot y dot z, x star y dot x dot y star z, with parentheses, x star y, one more star, x dot y star z. That's it. So now we can take the convention that we can omit dot, because the equation, first component of the equation tells us that the dot operation is just the associative operation. As the dot is associative. And now this is not a wonder that dot operation in our example comes from the multiplication of group. So the associativity is in there already. But now we can look at the relation 3. And one of the consequences of that relation was I think the pentagon wasn't used there. So 1 plus 3 implies R2 W to 1 R1 equal R1 W1 2 R2. Do you remember this an exercise? You had an exercise on proving that. Right? It was exercise. Now, if we write out this explicitly, so what we have? R2 W21 R1 applied to xy. So it is R2 W21. So x becomes with hat. Now, W21 is a permutation, conjugation by permutation. Permutation, W permutation. So we apply permutation. R2 permutation W to Y x hat. Now W, we know what is it. It's a dot and star. R2 P Y dot x hat, comma Y star x hat. Now we permute R2 Y star x hat, Y dot x hat, and we put a hat over second component, Y star x hat, Y dot x hat, hat. And now we apply to xy the right-hand side. Xy. So we put a hat over y. W x y hat. We apply w. R1 x dot x hat. X y y hat. And we put a hat over the first component. And look what happens. We observe by comparing the first component, or maybe second, better, because the x and y in right order. So we see that x star y hat is given entirely in terms of the product and the hats. Y, so I don't write the dot anymore. Hat, hat. And now we can replace, of course, y by y hat by y, just changing the notation. So x star y becomes a y check, x hat, hat. So effectively, we have reduced the whole data of a basic algebraic system in the category of set to a set with associative product and the one unary operation of order 3. And this unary operation gives us the second binary map. And what remains is what is the relation? What are the other relations? And we come back to relation 3. So the relation 3 tells us what. Let me rewrite it in more symmetric way, maybe. W to 1 R1 inverse. W equal R1 inverse, R2 inverse, P1, 2. So let us apply this now to x and y. So W to 1 R1 inverse, W xy. So we have a W to 1 R1 inverse x dot y x star y. I don't write dot anymore. W to 1 xy check x star y. So W to 1 is a conjugation by P. So P W x star y xy check. Now we use a W again. P x star y times xy check x star y star xy check, and P. P means exchange of two components. On the other hand, if we evaluate the right-hand side on xy. So it is a y check x check. So what we see is I'm not. I hope it is correct. So I have a little doubt, but let us substitute star. So a y check x hat check. So I think that this was is this correct? So can that's what I'm doubting now. Yeah, maybe it's correct. Let us. Okay, so hat. So this is a x star y. So I'm comparing the second part times x y check is equal x check. And the second thing, x check, y check, x hat. Hat star x y check is equal y check. And now we can use, and once more, the star in here. And I claim that it should reduce to the first relation. But I'm not quite sure because the formula can be wrong, but let us try anyway. So what is a star? So we put first the second argument with check. So it will be x, y, double check will be hat. Then we multiply first argument with hat. So y check, x hat, so double hat will be check. Right, and then we have to put one common hat. So this is the equivalent to y check. Yeah, it looks fine. So let us try. Now x we should replace by y check. And y we should replace by x hat. Let us do everywhere this substitution. So we get y check x hat hat. Now y check. So we put check. So we remove hat from here. So x hat. So we remove check from y, and check, and the hat should be equal. Y check should be equal y. Y check should be x. And this is the same thing as this. Right? So because this hat can be put as a check over x, and then we come back to here. So at least relation 3 now is satisfied due to this relation. And yeah, so it remains to check the pentagon, but the claim is that, so the claim relation 2, which is a pentagon, follows from let me call this star, double star, from star plus double star plus the condition that x times z equal y times z is equivalent to x equal y. So the cancellation property of the product. Because a priori this is not a group, so we don't have neither inverse nor the identity in the product. So, but if we demand that we can cancel the common multiple, then the definition of the star over there plus one single relation which mixes up the product and the hat operation implies the whole pentagon identity. So this I will not try to show here because it is a little lengthy. One part is maybe easier, but the other part is more lengthy. And I would like, so to prove our theorem, so it suffices then to check the double star relation. Okay, so, but first, of course, we check the star relation. So remember that x hat was x2 over x1, 1 over x1. So let us check. We have the star operation, so we have to check if this relation is satisfied. So what is x check? This is a x double hat. So I have to apply one more hat to here. So it is a x2, 1 over x1, divided by x1. So divided by this, x2, x1, comma, inverse of x1, x1 over x2. So this is the check. 1 over x2, x1 over x2. And triple check is identity. This is easy to see. And then I multiply y hat, y check x hat. So let us do that. So I replace this with y, 1 over y2, y1 over y2, multiplies this, x2, x1, 1 over x1. So we use the multiplication. So the first components are just multiplied, x2 over y2, x1, comma, 1 over y2 multiplies 1 over x1, and we add x2, which is here, y1 over y2. So what we can do, we can no, there is something wrong, right? Yeah, this is wrong. 1 over y2 multiplies the first component here, x2 over x1. So this becomes x2 or y2 x1. And the common denominator becomes y2 x1. And we have Yeah, I don't like the numerator here. X2 plus x1, y1. Oh, yeah, maybe it's okay. Now the last step is to take a check of that. Or check or hat. Y check, x hat. It was hat, right? So what we do? We take inverse Yeah, you see, we have to check of that. That's what I was suspecting. I did some way mistake. So if we take this will give the star operation. Look. So what we do? I invert second argument. So I invert this. y2 x1 divided by x1 y1 plus x2. And then what I do here, I multiply this by inverse of this. So then y2 x1 cancels out, and we end up with x2. It should be y, right? No. Sorry. So it's everything is wrong. Sorry. So let us postpone it to the next case, to the next time. I will start from that. So we will not arrive to the right answer. But this is right. But here something is wrong. So let us stop here. Sorry.